Hello guys, I'm Khalid Stepper. Welcome to Quality and Building Metallurgy. Today we are discussing on specific dissimilar metal and combination. Content: stainless steel to carbon steel or low alloy steel. Carbon migration, austenitic stainless steel filler metal, nickel alloy filler metal, service consideration. Specific dissimilar metal combination: stainless steel to carbon steel or low alloy steel. Austenitic, ferritic or magnetic stainless steel can be readily fusion welded to carbon or low alloy steel using a filler method that can be tolerate dilution by both base metals without formation of flaws in the joint. And austenitic stainless steel or nickel alloy filler metal is commonly used. The choice depends on the application and the service condition. Carbon migration. Carbon migration in steel has greater affinity for carbon than does chromium iron. When carbon or low alloy steel is welded with the filler metal contain a significant amount of chromium, carbon will diffuse from the base metal into the weld metal at temperature about 800 degrees Fahrenheit. The diffusion rate is function of temperature and exposure time and increases rather rapidly at 1100 Fahrenheit and above. Carbon migration can take place during post-weld heat treatment or service at elevated temperature. Austenitic steel has greater solubility for carbon than does ferrite steel. Therefore, carbon depend in carbon or low alloy steel is greater when an austenitic stainless steel filler metal. On the other hand, carbon migration is not problem when nickel, chromium, Fe, ferro filler metal such as type Fe-2 electrode is used. Sorry. If carbon migration is extensive, it will be indicated by light etching, low carbon band, and in the carbon steel heat affected zone in the stainless steel and the dark high carbon zone in the stainless steel weld metal as seen in transverse metallography section. The extent of carbon migration during post-weld heat treatment or elevated temperature service should be determined during welding procedure qualification. It is known to influence long-time stress rupture strain during elevated temperature service. During cyclic temperature service, the heat affected zone will be subjected to varying Shear stress because of the difference in coefficient of thermal expansion of the base metal and weld metal. This stress may be produce fatigue failure in the decarbonized when next to the weld interface. Austenitic stainless steel filler metal. A number of austenitic stainless steel filler metal are available commercially. The phase in the microstructure, the deposited metal from several of these filler metal are indicated one on the scapular diagram. In some cases, the microstructure is fully austenitic. In other cases, the microstructure will contain some delta ferrite. The amount depends on the alloy composition. Type ER 16-8-2 filler metal is recommended for well stainless steel piping system for high temperature service, but it is corrosion resistant is not good at the at as type 316 stainless steel. If weldment will be exposed to strong corrodent, the exposed weld passes should be made using a more corrosion resistant filler metal. Position of stainless steel weld metal on scapular diagram. Nickel alloy filler metal. A nickel alloy filler metal may be used to weld a stainless steel to carbon steel or low alloy steel. Those filler metal generally recommended for this application are type NiCi 2 or 4 covered electrode and type E NiCi 3 bare electrode and weld rod, but other nickel alloy filler metal are also suitable for application. Nickel alloy filler metal showed two transverse bent specimens of type 304 steel weld to mild steel, one with type ER NIMO 3 filler metal and other with 67 Ni 16 chromium and 15 MO and 2 cobalt, that is called Hastali as filler metal. They indicate the good ductility of nickel alloy filler metal. Service consideration. Give the main linear thermal coefficient as the function of the temperature for several alloys commonly associated with transition joint from steam plant application. The thermal expansion coefficient of 2/4 chrome 1 moly steel is about 25% less than that of the type 304 and 316 austenitic steel. In certain applications, transition joint between austenitic stainless steel and low alloy steel may experience numerous temperature change during operation. For given change in temperature, the stress imposed at weld joint to proportional to the difference in their coefficient of thermal expansion. Stress analysis of weld joint between these two types of steel indicate that the stress introduced by thermal change are nearly an order of magnitude greater than those produced by the operating pressure and any thermal gradient across the joint. When coefficient of thermal expansion as function of the temperature for transition zone alive. See the graph. Such with consideration, experience with dissimilar metal transition joint has shown significant number of failure in less than accepted service life. The number of transition joint failure in austenitic to ferritic steel joint occur in the ferrite steel heat affected zone adjacent to the weld interface. These failures are generally attributed to one or more of the following causes. First, number one, high stress and the resulting creep at the interface as a result of difference between the coefficient of thermal expansion of weld and base metal. Number two, carbon carbon migration from the ferritic steel into the stainless steel, which make which weakens which weakens the heat affected zone in the ferritic steel. Preferential oxidation and the interface accelerated by the process of stress. Presence of stress. A typical crack along the weld interface between austenitic stainless steel weld metal right and the ferritic steel base metal led to the fore. Thank you.